Somebody asked me this question, 4.4 Mindscape 5. We were making super tiles in class. We make a super tile by taking one of these parallelograms and putting 3 more parallelograms with it to make a larger parallelogram with 4 tiles. The way we did this in class then was to build the 4 tiles into 16 super tile, but that's not what they're doing on your homework question. On your homework question, they're looking for the next size up tile that you can make. So the next size up would be to use 9 tiles. So they're calling a super tile the 9 tiles. And that's the case for the parallelogram and for the triangles, because you can take 4 of these triangles and stack them up and make a triangle of the same proportions. You can also put one more row at the bottom here of 5, which we actually did in class, and make a larger triangle of 9 tiles. So the hint tells you the answer, but I'll tell you the answer too, okay? Because they're using the super tile phrasing a little differently than we did. Does anybody have any other questions? There's a reminder that you have study group Wednesday night, so that's tonight, so put that on your calendar to remind you, or else you can make an appointment for one-on-one help with tutoring. Some of the things that we do today do take practice. Tutors are a good place to get help with that. We're continuing in section 4.4. We've been looking at symmetry in a plane. If you don't have your slips of paper like this, can you please come up and get some? Or if you're at home, you can print some off from the Canvas homepage. You'll need 2. Okay, there's 2 different slips. So if you don't have them, come on up and get them. If you weren't here or you forgot yours. Yep, you need 2 different kinds. So we are looking at 2 kinds of symmetry. We looked at rigid symmetry, where you can take an overhead of the same, a transparency of the same pattern and translate it, or rotate it, or even flip it, and you should land up on top of the other pattern. So any one of these occurring, translation, flipping, or rotating and landing on top of the original pattern, is called rigid symmetry. All 3 don't have to be present, although the patterns we looked at had all 3 present. So rigid symmetry, you can slide a transparency around and land with the same pattern that you started with. Scalable symmetry was another type of symmetry.
I just have a question quick. You said that in order, you don't need to have all 3, the translate, flip, or rotate, just to be rigid. You can just have one?
Yep, so any of those. So any one of those. Scalable symmetry, on the other hand, you would need to be able to put tiles together to make the exact same shape and tile the plane in that way. So here we could put 4 tiles together in what your author calls a super tile. And if you put 4 of those together, you make a super tile, and you can keep going like that. So you can make 4 of these together for a total of 64 little tiles and have super tiles. And if you did that, when you took this shape and put it in a photocopier and shrunk it down, you would still have the exact same tiling pattern. So scalable symmetry means that as you put the tiles together that are small to make larger tiles, they make exactly the same shape. Exactly the same shape, and you can pattern the exact same pattern, just on a larger scale. So that was scalable symmetry. So we saw that these squares had both, the square tiling had both rigid symmetry and scalable symmetry. The hexagon tiling had the rigid symmetry, as you can see as I move this transparency about. But it had no symmetry of scale. No matter how I arrange these hexagons together, I'm not getting another hexagon. I'm just getting this kind of a flower shape, which is nice, but not symmetry of scale. So this hexagon shape had no symmetry of scale because I couldn't build a larger hexagon by just grouping the hexagons together that I had. The triangles had rigid symmetry and symmetry of scale. So you can see the rigid symmetry from sliding around the transparency, even if you're just doing that in your mind. And you can see symmetry of scale as you group together triangles to make a larger triangle, the same proportion. Anybody have any questions on the difference between rigid symmetry and symmetry of scale? You will need to be able to distinguish those, or tell if there's no symmetry at all. Before we left class on Monday, we had created a right triangle and looked at the symmetry you can make with that. So I put that into a Word document to talk about with you. So we'd put our right triangle together, and you helped me figure out how we could take the right triangle and make a super tile. And then once you have a super tile, you can use the same process to make a super tile. And here I have a super tile. This had symmetry of scale. It has symmetry of scale because we're building these super tiles from it. It also has rigid symmetry. If I slide a transparency around, the transparency lands on the original shape. Okay, so I can continue and tile the whole plane like this and see rigid symmetry going on. So rigid symmetry and symmetry of scale. Now the reason I draw that to your attention is because we have this other drawing. It doesn't look like that, but it's made out of right triangles too. So we made this one. It looks very nice. It has rigid symmetry and symmetry of scale. Very peaceful. This, on the other hand, is not peaceful. This is called the pinwheel pattern. If I try and lay the overhead on top of this and move it around, there's no way to move it and get the whole shape. Even just flipping it upside down, I think, messes it up. So I can line up a few triangles, but I cannot line up all the triangles. So we're going to explore why is this so chaotic looking compared to the symmetry of the one that we did with these right triangles. They're both collections of right triangles. This pinwheel pattern was created as an answer to a question that one of my students asked on the way out of class yesterday. Can a pattern have symmetry of scale without having rigid symmetry? Can a pattern have symmetry of scale without having rigid symmetry? So remember what we had seen. We had seen rigid symmetry with symmetry of scale with the triangles and with the squares. And we had seen rigid symmetry without symmetry of scale with the hexagons. But can we have it the other way around? So everything we looked at had symmetry of had the rigid symmetry. can we go the other way around? Can a pattern have the symmetry of scale, but not have rigid symmetry? If you try and make a scalable pattern like we did, are you always going to make something that has, if you make something that's scalable and has symmetry of scale, will it automatically have rigid symmetry? Well, the answer is no. And this is the response, this is the solution to that. It's called the pinwheel pattern. And it's a very particular right triangle. So let's go ahead and draw that right triangle and see how it's constructed. So use a ruler or graph paper, or I'm going to use lined paper as a ruler because I think all of you have lined paper, even if you don't have graph paper. We're going to look at the pinwheel pattern right triangle. So the pinwheel pattern right triangle is 1 unit tall and 2 units wide. So the base is twice as long as the height. Okay, so one of the legs of the right triangle is twice as long as the height is. So let me get a straight edge and make this a little neater, but you can use your lined paper to make 2 units wide. So you could have 1 graph square tall and 2 graph squares wide if you have graph paper, or 1 line tall and 2 lines wide. Let's see what the hypotenuse is then. So the A and the B are the sides making up the right angle. So when you're using the Pythagorean theorem, a squared plus b squared is c squared. The A and the B form the right angle. So that's 1 squared plus 2 squared equals c squared.
The square root of 5.
Good job. So the square root of 5 is c squared. Okay.
Easy.
Yeah, thank you. Square root of 5 is c. So the genius of this proportions is in how it allows the construction of the scalable property. So let's go ahead and make a super tile. So 2 units wide, 1 unit tall. Two units wide and 1 unit tall. And then we talked about how to make a right triangle into a super tile in class. So you had me flip this vertically. And stack it into a rectangle. So it's still 2 units by 1. Okay.
And 2 or 3?
2 units wide and 1 unit tall. And then you had me stack another one on top. and move one out front. Now this is a right triangle. It's lacking the correct proportions though. Okay, so if you take the pinwheels pattern right triangle, you look at the long side to the short side. By long side I mean leg. I should actually say long leg because the long side is the hypotenuse. So we'll say long leg to the short leg or short side. We have 2 to 1 or 2. Here we have, this is 2 units, this is 2 units, this is 1, this is 1. I guess this is this is still going to be, a ratio of 2 as well. That's interesting. I did not notice that. However, if we keep making super tiles like this, we're right back to the pattern that we did in class that has rigid symmetry. So we don't want to end up here. We don't want to keep building like this and get this rigid symmetry. So the genius in this is when the person who found this pattern added another triangle off to the side. So 1 unit, 1 unit off to the side, and it will be 2 units tall. So I'm making a triangle, still a right triangle with 1 unit for the short leg and 2 units for the long leg. There. But did we keep that correct ratio now when we added a 5th triangle? Let's check. Okay, so we had 2, 2, 1. So that makes 5. That's the hypotenuse though. That was the easy one to count off, but that's the hypotenuse. Okay, so each hypotenuse is square root of 5. For its length. So what is that, about 2.2? And we're not going to get the decimal, though we're going to use the exact values. So now my long leg is 2 square roots of 5. And the short leg is square root of 5. So that ratio is still 2. So I am being scalable. I am keeping the correct ratio of long leg to short leg when I scale this up. You're not making a scalable pattern if you change the proportion of your shapes. Okay, so your proportion of your shapes have to stay the same, and we see that that is in fact happening. So this pinwheel pattern gets this chaotic look from using 5 right triangles together to form the super tile. So let's go ahead and see if we can find 5 right triangles here. You should have one of your right triangles highlighted on this handout. Let's number these. This was our original 1, and then we went up, and then we went to the front, and then we went to the back. Okay? So we started with the 1 at the bottom in the center, and then we flipped it, then we went up one, and then we have a front and a tail. So looking at this, we want to see where it fits in relation to these triangles. So looking at this highlighted one, is this the front of it, this triangle right here? It kind of looks like it could be, except look at that, that's not straight. So that's not straight, so no, this is not the tip of the super tile that this is in. So this is in a super tile, but where in a super tile? What number is it? 1, 2, 3, 4, or 5 in the super tile that it is in? So it's 5?
Yeah.
The tail. Okay, so these are the 3 stacked up, and this is the tip. Okay, good. Nicely done. Okay, so now this is a super tile of 5. Let's see if we can find the super tile of 25 that goes with it. So remember that each of these should have 5, okay? So 1, 2, 3, 4, 5. In fact, one of the quiz questions that I'll ask you to do is to find a super tile of 25. So this is part of a super tile. What number is it in the super tile? Anybody see? Well, let's just see. Could it be number 1? Let's see. Number 1 has one flipped with it. It has one flipped with it, but the one that's flipped with it here makes a rectangle, and this doesn't make a rectangle. So it's not number 1 or number 2, because you can't make a rectangle with it. Could it be number 3? So number 3 is part of the hypotenuse. Would this be part of the hypotenuse? No, it doesn't. It doesn't look like it. How about number 4? Could it be number 4?
Yeah.
It could be number 4, so it looks like a tip. So it's this one. So we have 1. Always count off 5 to make sure you're getting 5. So you do have a stack of 3 to one side. So there's your stack of 3. 1, 2, 3 super tiles, and then you need one more super tile to make the tail. And that's it. Yep. Okay. So finding the super tiles is trickier than it looks, because you can find sets of 4 to make a right triangle. You can even find sets of 5 to make a right triangle. But if you don't find which set of 5 you're in, then it's hard to tell where you go. It just looks chaotic. So a quiz question would be, find a super tile of 25 smaller tiles. Outline each super tile. Outline each super tile. This does take practice. You can print off more copies from the Canvas homepage if you want to. And since it does take practice, it's worth more points than just multiple choice, okay? So because it does take practice, I'd like to walk around and see how you're doing and make sure you're getting the hang of it. Make sure you outline each super tile so that I can see if you're getting it or not, okay? So each, you should have 5 groups of 5. So you can count them off like we did here. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. If you get it, let me know and I'll come around and check, or if you're stuck, let me know. Otherwise, I'll just come around and see how you're doing.
I found like a different one that you have.
Yeah, you're supposed to find a different one. Good. Yeah, find a different one.
I don't know if it's a right angle right here. Like that.
No, it's not. Yeah, so that's why it's kind of tricky. So there is only one super towel that goes with that colored one. That's the one that we outlined. The triangle first. How's this going? Oh, you found a gigantic one. Let's see. 1, 2, 3, 4. Wait, is that 4? 1, 2, 3. Wait.
So
1,
it's
2.
all.
Oh yeah. Okay. There you go. Perfect. You have 1, 2. So this might be part of your stack, right? The stack of 3. So where would be 1 to finish the stack of 3 if you have that T shape? Let's see. At this at the that is definitely 1, but I don't think it makes the let's see, you have 1. Oh, this should go straight across there. Oh, okay. Yeah. So don't, here, wait. Just go to here and then it'll be places like, yeah, there you go. And then this line then should go like that. So this should be down there. Actually, this, wait, how tall did you use? You did yours 2 tall, and so hopefully this is, I'm not sure that is 4 wide. So if you did 2 tall, oh, so you did 2 tall instead of 1 tall.
Mm-hmm.
So it's not gonna work out actually.
Oh.
I can't bend over like okay, but I guess the original drawing would help you to so Do you have a piece of paper to use as a ruler? 11 line piece of paper from your nose?
Yeah.
There, is that one loose?
Never mind, that's
No, it's not tape line. Okay, or just a little peel off. This one?
1, 2, 3, 4, 5. 1, 2, 3, 4. Oh my God!
Did I find it? 1, 2, 3. Yeah. Alright, so we'll make it 1 line tall and just 2 lines wide. So just up to here.
I think I found one. Oh, no. Let me finish.
2 lines, yep, okay. Okay, so then, and then 1 line tall.
Oh shit, I think that's
So you just make it,
the
you can just straight up and out and make
a superset.
the hypotenuse.
1, 2, 3, 4, 5.
So it's just gonna go from here, 1 line tall to 2 lines wide. Whoops.
Dude, I can't. Oh shit.
That's what
I think I found you when you just been stupid.
Perfect, okay, so you see how it's 1 tall and 2 wide? Okay, and then if you go straight up, then you make another one flip that's also 1 tall and 2 wide, because you have a little rectangle. Okay, and then now this is 1 tall and 2 wide, so go connect here. And then this is 1 wide, so you can use your paper to measure. I mean, that was 1 tall, so you can use it. So here would be 2 wide. There you go. And you can make the hypotenuse again. And now this is 2 tall. So we'll make one wide. So there you go. From to there. Just 1, yeah. And then when you connect here, you have that 2 tall. Yeah. That. Okay. So what I was saying when you had those outlined is you have part of that stack. So you have let's see. You have these 2 together. That's this.
I think I was.
You need. There's like 3 stacked up here, and you have 2 together. You need 1 more. One more to make a rectangle with 1 of those. I think that one does. Okay, there you go. Okay, so you have this part going on. Now you need a tip and a tail.
Dude, is this
and
one?
I think you can find that there. That's not going to be. So the tip and the tail are on the 2 ends of it. So you have this part in
That's
here.
right there.
So you want to be on the front and the back.
It looks beautiful.
Yep, that's your tip. And then your tail. Oh, right here? Yeah. And now you can count those off. I don't know if you better darken that one or not.
I thought you had some.
Yeah.
Yeah.
Anybody else?
I don't think.
And then like.
I totally did this wrong. Because it's supposed to look like this, right?
Oh, you're almost there.
No, this is the one you had up there. This is the one I picked, but I think it's supposed to look like that. Isn't it?
Yeah, except this corner goes in there.
Oh, and then
And there's only 4.
oh. So I don't get what, when you were asking, when they pick 4, I don't understand.
I was just trying to orient which part of the triangle to be at.
Okay, so
Like,
but it's supposed to look like this, not like that.
correct.
Okay, so you got it like something else.
Yeah, yeah. If you get stuck.
Just flash.
Okay, all right, thank you.
Awesome.
Oh yeah, I see. It's very beautiful. This one I don't think so.
I'm just curious if there's one in between those two that you found.
Oh, this?
Yeah. That's what I'm checking.
Yeah, that's fine.
It'd be the whole thing.
Where would it be?
It'd be this whole thing in between the two. Because there's one here, one here, one here, one here, and one
Oh,
here.
yeah. This could make one too, right? I just like did this whole thing.
If you go up to here,
Yeah.
then it should.
Oh.
And there's one right here. If you connect this to that.
Well, where's the thing on behind?
This one.
Yeah.
Yeah, it
Will
has
you go to
that.
this one? Is this another one?
Oh, yeah, okay. Nice.
And then it should be
No, because you have to have groups of
one
five.
here.
Okay, maybe I don't understand. 1, 2, 3, 4. Oh, 5 triangles and
Because then you have the super one.
that makes
You
more
have one
sense.
more.
Okay, so with that in mind, so you can always get stuck and start in this tip down.
I'm not sure what it's doing.
Yeah.
Is there anybody who did that get looked at yet?
Yep. Should be straight down here.
This is your class activity, so once you have it, you can upload it. Okay, I'll come down there.
That would mess with the shape. Because without this, that's what we have to shape.
One more.
Oh, you're right. Never mind. Wait, that is a super right there.
Yeah. That's crazy.
Oh, that's the one that.
It's not bad, but it's talking about my social media news. So it's all about myself, so I'm just whatever you know.
Raise your hand if you think it looked at yet.
I feel like I kind of have this. No, that's
For like, like is it gonna be this
I want to compare.
It'll be this paper, I don't think I have a highlight on it. So it's exact piece.
So it's gonna be like, it's
Yeah.
gonna be the same pattern though?
We only need to find the one.
Oh, yeah.
It's 125.
These are 25, right?
Yeah. So you're gonna have to watch that because you might want to just count it off. Can someone look at yours? Anybody have any questions? If you get stuck, you can start in the front tip here. This is the same pattern that will be on the quiz. And count them off. If there's not 25 tiles in 5 tile groupings, then you've made an error. I'll do it in marker so you can see it better. So this is your class activity for 4.4. You can upload that if you have not yet. Sorry? How do I do that?
The paper so I can see the bottom.
Oh, thank you.
Thank you.
I got one with 125.
One with 125? Good.
Just kept going.
If you keep coloring, it looks very beautiful when you're done. Not so chaotic when you have colors. Well, I just told you there was no rigid symmetry, that it was impossible to slide a transparency around and have the tile land on itself. We'll take a look and see why is that. Why is there no rigid symmetry? So here's a transparency of one super tile and the original image. If we take the interior angle and try and put it in any of the other positions, the lines end up crossing for the other shapes. So for example, I have to flip it actually to get to line up with number 1, but when we do that, we see the lines crossing here. If I try and line the interior up with number 2, then the lines are crossing over here. If I take the interior and try and put it lined up with number 3, the lines are crossing here. And with number 4, we see the lines crossing again. So there's no way to line these up unless they're in the exact same position they start with and you build from there. So there is no rigid symmetry. There's an infinite number of orientations to these triangles because there's no rigid symmetry going on. They're all spiraling about in a pinwheel fashion. In math appreciation, we look at different aspects of math that mathematicians have found interesting, like we do in art appreciation. Sometimes in math appreciation, though, we like to see some of the real-life examples that result. These patterns, these symmetry patterns that don't have any rigid symmetry, in some cases, these exotic patterns reflect the geometric structure of a class of materials called quasi-crystals. So no rigid symmetry, but we do have a symmetry of scale in these quasi-crystals in some cases. We're going to move on to 4.5. So we continue looking at symmetry in 4.5, but we move into 3 dimensions. At the start of 4.4, I'd asked you for some symmetric shapes, and you had given me a number of symmetric shapes in 2 dimensions. How many symmetric shapes are there in 2 dimensions? And by symmetric here, I mean the same length sides and the same size angles. So you have your square, you have your triangle. I think somebody mentioned the octagon. How many symmetric shapes are there in 2 dimensions?
Isn't it infinite? Because you could just keep adding sides to
Good. Good. So you could make a regular polygon that has 100 sides. Or 1,000,000 sides. That would look very close to a circle, unless it was very large. So you're right, there's infinite. Infinite symmetric shapes in 2 dimensions that have the same length sides and the same size angles. When you look at your Platonic solids and when you were forming those for the class today, you became part of a long line of students studying the Platonic solids. So here you have a picture of the calligrapher and mathematician Johann I and Neudorfer and his son by Nicholas Neufchâtel. I think that must be Johann I. By Nicholas Neufchâtel in 1561. So there they are studying the Platonic solids, and you've joined a long line of students who historically studied the Platonic solids because of their beautiful symmetry. What you see with those Platonic solids in 3D is you see the same why don't I copy it down like I wrote it so it comes out nice. They have the same regular polygons for each side. Same regular polygons for each side, and the same number of sides meet at each corner. The same regular polygons for each side, and the same number of sides meet at each corner. Now, you made 5 of these Platonic solids, and my question is, how many are there? These are called regular solids. How many regular solids are there? For example, you made 3 regular solids, 3 Platonic solids that have triangles for their faces. Okay, one had 3 triangles meeting at each face. One had 4 triangles meeting at each face. One had 5 triangles meeting at each face, and they'd have to be equilateral triangles so that they're regular polygons, the same length sides and the same size angles. Can a regular solid have 6 equilateral triangles meeting at one angle? At one corner? Or you made a square cube there. You made a cube out of squares. You had 3 squares. Can 4 squares meet at one corner? So your construction of these hopefully helped you think about some of these ideas, and I'd like you to think about them further, okay? Can you make a regular solid that has 6 equilateral triangles, not just 2, 3, or 4, or 5? And can 4 squares meet at one corner, not just 3? So think about that, and we'll talk about it more on Friday. Bring your Platonic solids back then, please.